All right, we're going to do Chapter 5, Section 4, Integration by Parts homework. So let's start with this one. So they do this instead of the table that I do, so I'm going to change this around. So they say, what's U? And we usually let U be something that we take the derivative of and gets less complicated. So I'm going to put X there. And then they ask what dv is. That's this box down here. And so I'm going to let all the rest of this be dv. And then I'm going to figure out the derivative of u, which they wanted me to do, and I'm going to call that, see, the derivative of x is 1 dx. And then they want me to find v, the antiderivative of dv. So antiderivative of cosine, let's see, if I take the derivative of sine, I get cosine. But if I take the derivative of sine to get 2x, I'm going to have to do the derivative of sine of 2x, which would produce a 2. There's not a 2, so I have to divide by 2. Okay, so this goes there, this goes there, this goes there, this goes there. This is the way I like to set it up, so that the formula for integration by parts is the integral of u dv. That's what we're matching here. We called this u, we called this dv. By the product rule is u times v minus the antiderivative of v du. So we're going to do u times v, x times this one times this one. They're the diagonals in a table like this. Here it's u times v, the top row, so that's 1/2 x sine 2x minus the antiderivative of v du. So that's going to be 1/2 times 1 sine of 2x dx. So when we finally finish up, we've got this is inside the function, outside, so the 2's don't cancel. We get 1/2 x sine of 2x minus, we're going to get a 1/2 that pulls out, and the antiderivative of sine of 2x is going to be, see, we'd have to take the derivative of negative cosine 2x to get sine, but then it would be times the derivative of the inside, which would be times a 2, but there isn't a 2, so I'd have to put another 2 there, plus c. So I can write this as minus a minus, that would change to plus. So that my final answer would be 1/2 x sine of 2x plus 1/4 cosine 2x plus c. 2. All right, so I'm going to do my table. You can do it this way if you want. Again, usually when we're doing integration by parts, if there's an x out there, that gets simpler when we take the derivative. That's what we tend to let u be. And we let the rest of this be dv, derivative of v, the rest of it all the way through the dx. And if we find the derivative of x, it's 1 dx. The antiderivative of secant squared is tangent. But if I took the derivative of this, I'd get secant squared of negative 3x times the derivative inside, which would be times the negative 3. There isn't a negative 3, so I have to put a negative 3 down to cancel the negative 3 that would show up when I took the derivative. So this is here, this is there. Antiderivative of this is, the derivative of this is 1 dx, and the derivative of the antiderivative of this is this. So the blue goes here and the other blue goes there. So this turns into, and once again we're referring to our integration by parts formula that comes from the product rule. We take our u times v, x times tangent of negative 3x divided by negative 3, that's u times v, minus the integral of not u dv, but u v du v. So this would be negative 1/3 tangent negative 3x times 1 dx. So I get all of this. I'll just write negative 1/3 x tangent negative 3x minus, and that would be a third, and the antiderivative of tangent is what? Well, we need to go to our substitution, a problem that we didn't get to in the last one. We're going to find the antiderivative of tangent. So I'm going to step aside and do that using substitution. So if I need the antiderivative of tangent of x, tangent is sine of x over cosine x. And if I want to solve this by substitution, if I let u be sine x, then I'd get a sine x under the du, and the sine x's would cancel. Or I'd get a cosine x, and I'd get a cosine x, which wouldn't cancel. If I let u be cosine x, the derivative is sine, negative sine, and I would, solving for the du, it would end up with a sine underneath that would cancel. So I let, I'll just show you here, u be cosine x. Then the derivative of u is, derivative of cosine is negative sine x dx. So this would become the antiderivative. Didn't use not a sine x, so I'm going to write the sine x. I have a cosine x, which I'm calling u, and I have dx, which I can see is going to be du divided by negative sine x. And since the sine x that varies cancels, basically I just have minus the antiderivative of 1 over u du, which is 1 over u, antiderivative is ln u. But u was the cosine, so it's minus ln cosine of x plus c. Now, if you were to look at a table, you wouldn't see it written this way. Now, what you would see is a minus 1 can go up as a power and change it to cosine to the negative 1, which means the cosine would go in the denominator. And 1 over cosine is secant. So a table would tell you that the antiderivative of tangent is ln of secant of x. Now, I didn't do that step in class today, showing you that, but so I can go down here and say, okay, I got 1/3 the antiderivative of tangent, which will be ln of secant of my angle, which is negative 3x. But if I took the derivative of that, I would get tangent and times a negative 3, so I have to divide everything by a negative 3 plus c. So I end up finally with negative 1/3 x tangent negative 3x minus a minus plus 1/9 ln of the secant negative 3x plus c. Now, if you didn't do this last step, this could be minus 1/9 ln of cosine of negative 3x. Either answer should work if you type it in on this program. Okay. So here, just looking at it to start with, you would think, oh man, I'm going to do integrations by parts 10 times to go from x to the 10 to the 9 to the 8th, because this is what we usually let u be. And if I put x to the 10th there, it would go to x to 10x to the 9th in its derivative. Fortunately, it works out well if to not do that, but to put that in for u. And another reason is we haven't talked about what is the antiderivative of ln of 4x, or antiderivative of any ln. So we really don't want to put ln there. We're going to put the ln of 4x here, calling this the u, and everything else the derivative of v. So then I got to figure out some derivatives and antiderivatives. The ln of 4x is 1 over 4x, derivative of natural log is 1 over whatever it is up, times the derivative of the inside, which should be times a 4 dx. The 4's would cancel, so really it's just 1 dx divided by x. And the antiderivative of this we'd have to add 1 to the power, so that'd be x to the 11th divided by 11, or times 1/11. So u was the ln of 4x, dv was the x to the 10 dx. Du would be the derivative of this, which we decided was dx over x, and v is 1/11 x to the 11. So the formula is uv minus integral of v du. uv is ln of 4x times 1/11 x to the 11 minus the blue, the ones we created, not the ones we started with. So we'd have the blue, which would be dx over x and 1/11, which can be pulled out, of x to the 11th. One of these x's cancels that and change that to x to the 10th. And now we do the antiderivative, which is 1/11 ln 4x times x to the 11th power minus 1/11, and the antiderivative of x to the 10th, it was 11, but we canceled one, so made x to the 10th, is x to the 11th over 11. Dx is, we're taking care of, plus c. You could type it in this way, but let's clean it up a little bit. So it would be 1/11 ln 4x times x to the 11th minus 1 over 121, 11 times 11, x to the 11 plus c. Now, the book might, in the answers, might factor x to the 11th out and maybe factor out 11 in the denominator, so this would be 1 and this would be 1/11 here, but you don't have to. Okay. Now we just got to do one here. And so I see something that'll get simpler if I put that in u. If I put t there, then the derivative would be, derivative of t is 1 dt. And if I put v here and do the rest of that as v, the antiderivative of that would be e to the negative t, but there would be a negative that shows up. If I took a derivative of e to the negative t, it would be e to the negative t times the derivative of that, which is -1. I don't want a -1 because there wasn't a -1 out there, so I have to put a -1 to cancel that -1. You could put it underneath or put it in front. So this becomes uv negative t e to the negative t minus these two. And that's going to be the antiderivative of negative 1 times e to the negative t dt. So, and this doesn't cancel, those negatives don't cancel, so this is negative t e to the negative t plus the antiderivative of e to the negative t is e to the negative t divided by, or yeah, divided by the negative 1 that you would get there if you took the derivative, plus c, and you can write this negative right there if you want. Okay, this one. I think if I put y here, it would get simpler when I took the derivative. In fact, the derivative of y would be 1 dy. And if I put the rest here, y plus 2 to the 1/3 power dy, I'd have to figure out the antiderivative of this. So I'd have to add 1 to this, so it'd be y to the 4/3, y plus 2 to 1 bigger than 1/3 is 4/3, 3/3 more, divided by 4/3, or times 3/4. So it's uv 3/4 times y times y plus 2 to the 4/3, uv minus the integral of those two. So it's 1 times 3/4. That part can be pulled out. And then left would be y2 plus 2 to the 4/3 dy. We'd have to integrate it. Now, when I did the antiderivative here, I didn't worry about the 2, because when I take the derivative of this, I take the 4/3 down times this to 1 less, which would be the 1/3, and then times the derivative of the inside, which would be just 1, because the 2 would disappear on that. So same kind of thing happens here. I don't really have to worry about that plus 2. So I get 3/4 y plus 2 to the 4/3 minus 3/4 antiderivative of this. I add 1 to this, which is 3/3. So that turns into y plus 2 to the 7/3, or 2 1/3, plus, and divide by that. So divide by 7/3, or multiply by 3/7. So finally I get 3/4 y plus 2 to the 4/3 minus, I invert and multiply, 7/3, the 3's canceled, so I get 7/4 y plus 2 to the 7/3. Okay, that's 5. Let's go to 6. I think I'm going to put this in the u, because if I take the derivative of that, it pretty much turns to 1. So in my table, I'm going to put z plus 1 under the u, and the rest of this under the dv, the derivative, not the function. So that would be e to the 6z dz. Derivative of z plus 1 is 1 dz. And the antiderivative of e to the 6z is 1/6 e to the 6z. Because the derivative of this would be the same times the derivative of that, which would be a 6. That cancel the 6 and be just that. All right. uv, these two multiplied, 1/6 times z plus 1, 1/6 times z plus 1 times e to the 6z minus the antiderivative of these two, which is 1/6 e to the 6z dz. Now I can factor out the 1/6, but I'm not going to. I'm just going to write it's going to be 1/6 z plus 1 e to the 6z minus 1/6, and the antiderivative of this is going to have a 1/6 e to the 6z. So this would be 1/36 e there, and that would be all I would change if I wrote that. Okay, the one that was bothering some people in class. It's a fairly challenging one here. So I'm going to do this one on a separate piece of paper because it gets a little bit long. So we would normally think to make u be this and this be dv. And that's what we are going to do. Now we could put this in the u and take the derivative of it. We know that. And then do the antiderivative of the x, which would be x squared over 2. But that makes it more complicated. So we're going to do it just like we've been doing. I'm going to put the x here for the function. Its derivative would be 1 dx. And I'm going to put the arc tangent 6x dx in that spot. So I need to know the antiderivative of arctangent of x. And we haven't, let's see, have we done that? Let's see. We have to do that to do this problem. So that is a substitution problem. So we're going to go off to the side and try to figure out the antiderivative of arc tangent 6x. All right, not substitution, but this is a integration by parts separate problem. It's in the activities or exercises above this, the homework on this. So I'm going to do my table for this. And I'm going to put the arc tangent here. And put just the dx down there. u, v, the function, its derivative. I'm going to figure out these two. Derivative of arctangent is 1 over 1 plus whatever the variable is, squared, times the derivative of the inside, which is a 6 dx. And the antiderivative of 1 dx is just x. So using integration by parts, we do u times v, x, arctangent 6x, minus the antiderivative of the red, which is 6, 1 over 1 plus 6x quantity squared, which is 36x squared, times x dx. Now, if we do a u sub on this, letting u be that denominator, 1 plus 36x squared, du would be the derivative of this, which should be 72x dx. So this would stay x arctangent 6x minus the antiderivative. I have a 6 on the outside. I have an x in the numerator. I'm calling that u. And I have dx, which is du over 72x. The x's cancel. So I get the antiderivative of this original thing is x arctangent 6x minus 6, 1 over u's and a 72 comes out in the bottom. Yeah, 72. Checking things here. Antiderivative of 1 over u is ln u, and u was so get that out of there, plus c. So all of this would go there. The antiderivative of this would be all of this, which is a horrid mess. X arctangent 6x minus 6 over 72 is 1/12. Natural log of arctangent 6x and so to do this, it would turn into u times v, so this times all of this, x times x arctangent 6x minus 1/12 ln arctangent 6x u times v minus the integral of this times this. So it'd be has a dx here and a 1 times all of this. So it'd be x arc tangent 6x minus 1/12 ln of arc tangent 6x. I'm not liking this very much at all. And this could be split up. This could be the integral of this dx and minus plus the integral of this dx. This is what we started with. So we could add that to this side, and we get 2 of these would equal this minus plus 1/12 antiderivative of this. And that is not very nice. So I must be missing something, because this is way too complicated for you. So we'd have to still integrate that. And I don't see how to do that. Now, the way you normally would have set this up, if we'd been doing just what we've been doing all along, would have been to do that. Let's just try it again here the other way, just so that you know that I am persistent like I'd like you to be persistent. UV, if we just put the x there, no, that's what we were trying to do. If we'd put the arctangent here, 6x, I don't think this works out very well, but we'll see here. And we'll put the x dx here. So the antiderivative of this is 1/2 x squared. And the derivative of this is 1/1 plus whatever's x is squared. So that's 36x squared times the derivative of the inside, which should be a 6 dx. So the antiderivative of this would be this times this, 1/2 x squared arctangent 6x minus the antiderivative of these multiplied. So we'd have 6/1 plus 36x squared times this 1/2 x squared and the dx. And this 6 could come out and be out here. And that doesn't work very well with substitution. Or any other method we have. So the ending answer for number 7 is, I don't think we should do that one. Okay? I think we'd have to do trig sub to solve that one, which is something we're going to get to. Okay. This one would work with integration by parts. You just have to do it twice. The first time letting u be this, second time it'd be even lower. This one you'd let you would do let u be ln of 7x and then 2, yeah, and dv would be just the dx, ln of 7x squared. and you'd put that in the derivative. So those will work out. Okay,